Like all other mammals, cows give birth to their young as live babies. In that respect, they're biologically similar to humans. But there's another similarity which may surprise you. For a typical cow, the duration of its pregnancy is about 9 months. Again, practically the same as for humans. Now, is that just a coincidence, or is there a deeper relationship? You can't tell just from that single figure, the average, because there are some pregnancies shorter than 9 months and some longer, both for humans and for cows. The way you can get more information is by looking at more detailed data, the duration of pregnancy for a sample of women and for a sample of cows. If we do that, we might start to see some differences. This histogram represents 1 year's admissions into the Princess Mary Maternity Hospital in Newcastle. As you can see, the most common duration is 40 weeks, but there's quite a spread. We've another histogram representing data for cows, collected for the Milk Marketing Board at several agricultural research establishments. Again, the most common duration is about 40 weeks, just over 9 months. But the spread of the data doesn't seem so high. You can see this more clearly if we compare the two histograms. We've chosen the same horizontal scale, and you can see that the two peaks are in the same place. But you can also see that the spread is rather different. For cows, births are spread over a range of less than a week, whereas for humans, the range is as much as 15 weeks or so. So, there are two features of the histograms we can use when comparing sets of data: the location and the spread. And although there are several different ways of measuring these features, we use the mean to measure the location and the standard deviation to measure the spread. For these human pregnancies, the mean is 39.2 weeks and the standard deviation 2.6 weeks. Whereas for cows, the mean is 40.2 weeks, very similar, but the standard deviation is 0.7 weeks, a lot less. So the histograms in these two situations do show a marked difference. But in fact, we know that the underlying mechanism for pregnancy in mammals is essentially the same, although the details differ considerably. So, although the data sets are different, we might look for an underlying similarity, irrespective of whether the means are the same or not, and whether the standard deviations are the same or not. What we need to do is find a way of comparing sets of data which ignores possible differences in the mean or the standard deviation. To ignore the influence of the mean, we adjust the data so that it's centered around 0. Changing the mean hasn't affected the standard deviation. It's still 2.6. But now we can change the scale of our measurements so that the standard deviation becomes 1. We can do that for our other set of data. Change the location so that the mean becomes 0. Then change the scale so that the standard deviation becomes 1. And now we can compare these two data sets. And in fact, they're still not all that similar. But by eliminating the mean and standard deviation, we can concentrate on the shape of the histogram. We can see now that these two histograms have somewhat different shapes. Now, that's a technique that can always be used. We call it standardization. What we do is replace each data value by a new one, using this formula. We subtract the mean, that's a translation, and then we divide by the standard deviation, that's a scaling. Once we've standardized our data, we're then no longer distracted by differing means and standard deviations, and we can concentrate on the shape of the histogram. But does the shape of the histogram actually mean anything? How do shapes vary? One way to find out is to look at more sets of data.
In 1950, the Clothing Industry Development Council initiated a survey to determine women's measurements and sizes. They took a sample of nearly 5,000 women and made 37 different measurements on each woman. The results were published by the Board of Trade in 1957. I've drawn the data from 4 of those measurements into histograms. The first measurement was height, and this is the histogram before standardization. The mean is 159.6 centimeters, about 5'3", and the standard deviation is 6.59 centimeters, that's about 2.5 inches. Obviously, height is important for the clothing industry. Manufacturers need to know not just the height of the average woman, but the range of different heights and how they're distributed. But height isn't the only vertical measurement. You can have people with the same height, but with, say, different body lengths. So the survey looked at several other vertical measurements as well. One of them is called the trunk line. That's the length from just under the arm to the waist. And here's the histogram. The mean is 19.5 centimeters and the standard deviation 2.18 centimeters. We've plotted this histogram on the same scale as the one for heights. Its location is quite different. Of course, horizontal measurements are just as important as vertical measurements. One is the distance across the back between the shoulder blades. It has similar characteristics to the vertical measurements in the sense that it's measuring bone distances and doesn't take account of layers of flesh that might otherwise be involved. In this case, the mean was 33.6 centimeters, the standard deviation 2.91 centimeters. The fourth measurement was the waist girth, the measurement all the way round the waist. Of course, this measurement is considerably affected by fat, and as a result, the histogram does look slightly different. It seems a bit lopsided. The mean was 67.8 centimeters, and the standard deviation 8.88 centimeters. So now we've prepared 6 histograms, but I'm going to include 2 more. When we were looking at the Poisson process in Unit 5, we counted the numbers of vehicles passing a fixed point in a given length of time. When the traffic was flowing freely, we expected a Poisson distribution. And this is the histogram we obtained. It's different from the others in the sense that the columns represent counts rather than measurements. That's to say, it's a discrete distribution rather than a continuous distribution. But we can still talk about its shape. The mean was 3.1 vehicles and the standard deviation 1.7. In the same experiment, we measured the time intervals between vehicles travelling on the road. These really were measurements rather than counts, although we grouped the measurements together for the purpose of drawing histograms. And this is the histogram, clearly lopsided, with many more small measurements than large ones. The mean was 9.9 seconds and the standard deviation 9.8 seconds. So now we've got 8 histograms altogether, and that'll be enough for our purpose. Some of them come from different situations, and in the same situation, we might be collecting different measurements. What we want to do is to find some way of classifying their shapes. We already know that we can't do this just by comparing the histograms, because they have different means and standard deviations. With the pregnancies, we had to standardize. So let's standardize the other 6. Now, these are the standardized histograms, all with mean 0 and standard deviation 1. We've also chosen the vertical scales so that in each case the area under the histogram is 1. And now we can ask our question. Do all the histograms have the same shape? Clearly they don't. For a start, some of the histograms look symmetric, whereas, as we've already pointed out, others are rather lopsided. As we say in the trade, they're skew. For example, this histogram of times between vehicles is highly skew. There are lots of values to the left of the mean, which we've set to be 0, but only a few to the right. Again, look at the waist girth measurements. There are more values to the left of the mean than to the right, though the skewness doesn't seem as marked as with the vehicle times. By contrast, look at this one. Durations of human pregnancy. This histogram is skewed the other way. There are more values to the right of the mean than to the left. And this is the histogram of height measurements in our sample of women. I can't tell by looking at it whether it's skew at all. So that's one difference between the histograms. They have different directions and amounts of skewness. But skewness isn't the only thing one takes into account. There's another feature you can distinguish. Compare these two measurements in our sample of women. On the left is the distance across the back. On the right is the measurement round the waist. The histogram on the right is noticeably more pointed than the one on the left. Even after standardization, there are more values clustered round the mean on the right-hand histogram than on the left-hand one. We've said that this histogram is more pointed than the other. In statistics textbooks, you might find the word kurtosis used for this feature, but we'll use the more descriptive word pointedness. So that's another distinguishing feature, the pointedness of a histogram. Of course, we don't really find the skewness and pointedness just by looking at histograms. In fact, we calculate them, and we use exactly the same idea as with the mean and standard deviation, the idea of averaging.
Of course, you've used averaging to calculate the sample mean, and the standard deviation also came from an average. We took the average of the squares of the deviations, and then the standard deviation was the square root. But now we've used the mean and standard deviation to perform a translation and scaling on each data point. That now means the average of our transformed data points is 0, and the average of their squares is 1. But we've seen the shape is still shown by our standardized data, and we can continue to use the idea of averaging to measure it. The average of z cubed gives us a measure of skewness, and the average of z to the 4th power gives us pointedness. Well, that's just a bald statement. Why does it actually work? You can see why by looking at some of our data sets. We've arranged a display of the standardized histogram for the time between vehicles. As you can see, we've got a large number of small negative values, and they're balanced by a small number of large positive values. The word balance is a good one. It really is just like a balance. Now, what's the skewness for these data? For a data point z, we said we'd look at the average of z cubed. Now, we've got a large number of small values on the left. When you cube them, they'll stay small, or perhaps get even smaller. But when you cube the large values on the right, they'll get very much larger, and they'll overwhelm the small values. The skewness will be positive because of the long tail on the right. In fact, the skewness is 1.75. By contrast, let's do the same thing to this symmetric-looking data set, the one showing heights. You get large positive values by cubing the tail on the right, but then you get large negative values by cubing the tail on the left, and they cancel out, or very nearly. We can do the calculation and find the skewness is actually 0.13, and that's a whole order of magnitude less than the last one, which was 1.75. So, the average of the cubes measures the skewness of the data. In the same way, the average of the 4th powers gives us the pointedness. Now, of course, 4th powers can't cancel out, because they're always positive. So the pointedness will always be positive. but you still get a range of different values. For example, look again at the histogram for heights. If we get the computer to calculate the pointedness, the result is 3.15. By contrast, look at the histogram of waist measurements. In fact, there's a sharp peak in the middle, and that means fewer values in the middle and more in the tails. So this time there are large values to be raised to the fourth power, and the pointedness will be larger. We can calculate the pointedness of this histogram. It's 5.08. And you can do this with any set of data. Standardize it, then work out the skewness and pointedness. Here it is for all 8 of our data sets. But it doesn't help us compare them very easily. The comparison becomes much easier if we can plot these pairs of numbers on a graph. We'll plot the skewness of each histogram along the horizontal axis. And the pointedness will be along the vertical axis. Now, here are the different sets of data. And the interesting thing is this. 4 of the points are spread out, but 4 of them are very close together, with skewness about 0 and pointedness near 3. Now, is that something of which we should take particular note?
As we'll see, it's no accident that several of the histograms had skewness near 0 and pointedness near 3. There's a very important probability distribution which gives us those values 0 and 3 exactly. Now, it's not one you've met so far in the course. We can check on this by looking at some of the distributions you have met. What we'll do is to show you each distribution with different parameter values and plot the skewness and pointedness on our diagram. We'll start with an old friend, the Poisson distribution with parameter mu. This Poisson distribution has mu equal to 4, and it's got skewness 0.5, pointedness 3.25. If we decrease mu, both skewness and pointedness increase. The curve we get is part of a parabola. And if we increase mu, the skewness and pointedness decrease until we approach the point 0,3. Other distributions give us other curves. The binomial distribution with n equals 1 gives us this parabola. Increasing n gives us a family of parabolas. The negative binomial distribution also gives a family of curves, depending on the parameter r. This time, we just get sections of parabolas. And in the simple case when r equals 1, corresponding to the geometric distribution, this is the curve we get. So far, we've only considered discrete distributions. Now let's look at a continuous distribution, the exponential. Exponential distributions have the same general shape as geometric ones, so we'd rather expect to find the skewness pointedness plots for the exponential distributions lying somewhere near the geometric parabola. In fact, there's just one plot, the same for all exponential distributions. It's at the point skewness 2, pointedness 9, at the very end of the geometric parabola. So how do these plots for the skewness and pointedness of distributions compare with the skewness and pointedness of the data sets we had before? In the case of free-flowing traffic, we can construct a probability model, a Poisson process. So, looking at the data about the number of vehicles in a time interval, we'd expect to get a dot near the Poisson parabola. And that's just what we do get. Again, looking at the time between vehicles, we'd expect to get a dot near the position for the exponential distribution. Once again, that's what we do get. But those are distributions we know. What about our quest for a distribution with skewness 0 and pointedness 3? We've found distributions which get close to it, but we haven't found one which actually hits that point exactly. But there is one which does just that. It's so famous that it's called the normal distribution.
And here it is. This is the probability density function of the normal distribution. It has two parameters, mu and sigma, the mean and the standard deviation. If you choose mu to be 0 and sigma to be 1, the graph of the PDF looks like this. It has a characteristic shape. Some people even think it looks like a bell. You'll notice that it's symmetric about the mean, and that most of the probability is concentrated in this region within 3 units either side of the mean. You can calculate the skewness and the pointedness of the normal distribution. You'll find the skewness turns out to be 0 and the pointedness 3. Exactly those values we're looking for. And if we compare this curve with our data sets, then we can see how well the measures of skewness and pointedness can guide us to a close-fitting distribution. Human pregnancies. Not very good. Pregnancies of cows. That's rather better. Women's heights. Very good. And that was one where skewness and pointedness were near 0 and 3. Trunk line. Very good again. Distance across back. Still fairly good, though the histogram's fairly jagged at the top. Waist girth. Not very good at all. And from the skewness and pointedness, you wouldn't expect it to be a good fit. So, what's the lesson we can learn? This new distribution, the normal distribution, is a good fit to many sets of data, but by no means to all. It's a good approximation to several other distributions, such as the Poisson and the binomial, but again, in certain circumstances, not always. It always has skewness 0 and pointedness 3. And if the same applies approximately to the data, it could well be a good fit. And if you wonder whether this ubiquitousness of the normal distribution is an accident, of course it's not. And in a couple of units' time, you'll meet a theorem which explains just why the normal distribution is such a common one.